Okay. Hi guys. So today is going to be our last lesson on Unit 1. So we'll finish off all the homework problems that were assigned to you yesterday, and then for the next class we'll have a unit test. Now for those of you watching online, I have everything uploaded onto Google Classroom. So in a couple of days you'll be able to see a PDF file of the unit test along with the answer key. And in next class, we'll go over the answers and explanations to that unit test. But first, let's review all the homework questions that we did that was assigned last class. So we start with number 8. So this is chapter 1-2. Function f of x is continuous on the set of all real numbers and satisfies x minus 1 times f of x equals x squared plus x minus a. And then find f of 1. Okay, now if you directly try to plug in 1, the immediate issue is that this whole left-hand term goes to 0, and basically it also sends f of 1 to 0, right? So we can't directly plug it in and figure it out, but we have to use the fact that f of x is continuous, right? The function value of f of 1, so f of 1 is equal to the limit value as x approaches 1. So if we rearrange this expression into x squared plus x minus a over x minus 1, like that. Now, by dividing by x minus 1 on both sides, I am implying that whatever x is, x is not 1. But we're allowed to do that, right? We're allowed to do that because we know that when we take the limit as x goes to 1, we're not actually getting to 1. So we can say that f of 1 equals limit x goes to 1 of f of x, right? The limit equals the function value. That's the very definition of continuity. Okay, and now this must exist. Now, find the value of f of 1, so this limit must exist. If we plug in 1, the denominator goes to 0, which means that the numerator must also go to 0, right? That was a theme that was emphasized throughout chapter 1-1. So 1 plus 1 minus a equals 0, a equals 2, and then we go back to the limit, we plug it in, x goes to 1 of x squared plus x minus 2, x minus 1, and then we can factor it 1, 2, minus, and then so that goes away and leaves you with x plus 2, so that's 1 plus 2 equals 3, and that would be your final value of f of 1. Cool. On to number 9. Two functions f of x equals x squared plus ax, so that's x squared plus ax, and function g of x is defined as, so 1, negative 1, 1 when x is greater than 0, and negative 1 when x is less or equal to than 0. Find constant a, so that function, okay, we got a composite function, f of g of x is continuous at x equals 0. Okay, so g of x is obviously not continuous at x equals 0, and that creates a potential point of discontinuity. F of x is a smooth parabola, polynomial function, so there's no potential points of discontinuity on just the outer function. So what we really need to focus on is the function at x equals 0. Okay, so we need to consider 0 plus, and at 0 minus it's coupled together with the function value, right? We see the equal sign here. So we can say 0 minus and 0, we only need to consider these two. At 0 plus, we have f of 1, right? So f of 1, since the output of g is 1, the input of f is 1, 1 plus a, that's the function value, and at 0 minus and at the function value 0, we have f of negative 1, which is 1 minus a. And it has to be continuous, so that these two have to equal each other. 1 plus a equals 1 minus a has to equal 0, and that is your final answer for this one. Okay, moving on. Number 11. So we have a piecewise for f of x. Function f of x is defined like so. X squared minus 4x plus 6 when x is less than 2, and 1 when x is greater or equal to than 2. Find constant a. Okay, so g of x equals ax plus 1. And now we have to say that g of x over f of x has to be continuous for the set of all real numbers. Okay, so couple of things here. So the denominator is what we have to look out for, right? G of x is a linear function, so and it's on the numerator, so we really don't need to care about any discontinuities there. Now, f of x, we have a discontinuity at x equals 2. That's when the function changes, right? Yeah, the function changes because the left-hand limit at x equals 2 is 4 minus 8 plus 6, which is 2, right? 4 minus 8 plus 6 is 2, and then this is 1, so they don't match each other, and that's a discontinuity at x equals 2. We also need to think about, because it's a rational function, are there any potential values where f of x equals 0? And we need to look at this quadratic here, right? Now, if we look at the discriminant of this quadratic, we can use a simplified discriminant if you want. And that equals negative 2 squared, right? Negative 2 squared minus 6, and that equals negative 2. So it's actually less than 0. So if you guys don't know what the simplified discriminant is, it's when you have a even coefficient, an even integer coefficient at x. The simplified quadratic equation is actually a and negative b prime. So you take whatever the even coefficient is and you divide it by 2, plus minus square root of b prime squared minus ac, and this can really reduce your burden of calculations. And the simplified discriminant is just b prime squared minus ac. If you want to prove this, just plug this into the original quadratic formula and you should get this result. Okay, anyway, the discriminant is less than 0. That means there are no points because it's a concave up parabola. It will be like that, right? It will not be touching the x-axis, so we don't have to worry about when the denominator is 0. So just like carefully checking through these things is a really good habit to have, right? You don't really want to rush through and miss potential important points. Okay, so it needs to be continuous. All we have to check for is the boundary at 2. So at 2, g of x, let's go to 2 minus, then f of x is going to be what? 4 plus 6 minus 8, so that's 2. And then g of x is going to be 2a plus 1. And at 2 plus and 2, right, it's the same thing. F of x is going to be 1, and g of x is going to be 2a plus 1. So that's just 2a plus 1, and these two have to be equal to each other. So 2a plus 1 equals 4a plus 2. So 2a equals negative 1, a equals negative 1/2 would be the answer to this question. Okay, number 12. Function f of x equals, we have another piecewise. We have a pretty peculiar condition here. It's discontinuous at x equals 0. Okay, so we got a condition on discontinuity. X plus 2, negative x plus a, x is less or equal to than 0, and x is greater than 0. So it's discontinuous at x equals 0. But it also says that function f of x times f of x minus 1 is continuous at x equals 1. Okay, find constant a. So we have two conditions given to us. Let's take a look at this one first. At x equals 0, the left-hand limit and the function value is 2, and the right-hand limit is a. Now, usually we would want this to be equal to each other if it were continuous, but since it's discontinuous, we have to make sure that a does not equal 2. So that might be useful later on. And now we can look at the second condition, which is the more familiar one that we've been dealing with. F of x minus 1 at x equals 1. So let's go 1 plus. At 1 plus, it's f of 1 plus. So that's obviously greater than 0. So we go negative 1 plus a, and then at 1 plus, x minus 1 is going to be what? 0 plus, right? 0 plus is on this side. So that's as x goes to 1, right? So that's negative. Oh, sorry, so it's f of 0 plus, so it's just a, right? We plug in 0, and that's just a, since it's f of 0 plus. Okay, at 1 minus, 1 minus f of 1, that's still negative 1 plus a. And at 1 minus, it's going to be 0 minus, so we go over to the top equation and plug in 0 times 2. And then the function value itself will be f1 times f0, which will also go to here. So this is at 1 and 1 minus. So these two have to be equal to each other. Okay, so 1 minus 1 plus a times a equals minus 1 plus a times 2. And then we can, remember, we really don't want to cross things out unless we guarantee that they're not 0. So I'll keep them for now. And then we go a minus 2 equals 0, and this is a quadratic factored equation. So a equals 1 or a equals 2. And now this is where our discontinuous condition comes in handy, because we just said that a cannot equal 2 to ensure that this function is discontinuous at x equals 0. So this would be an invalid solution, and our final answer is a equals 1 only. Okay, so that was number 12. Let's go to the next one, number 14. So number 14, we have a three-way piecewise, but it's pretty, I think it's pretty simple. F of x equals negative 1, and x, negative x, and 1. So it's negative x between negative 1 and 1. When it's less or equal to than negative 1, it's negative 1. Then if it's greater or equal to than 1, it's 1. Select all limits that are true. Now, I'm really a fan of visual reasoning and trying to imagine and sketch what's going on might really help you, especially when you're solving some more complex questions. But even in simple cases as this one, we can quickly sketch it, right? So 1, it's negative 1 until negative 1. So we go negative 1 comma negative 1. And it's like that, right? And then it's negative x between. So we have a closed hole here and an open hole here, right? To 1, and then we have a negative x graph until 1 comma negative 1. And then at this point we go to 1 comma 1. We have a closed hole here. And this is the graph of f of x, right? F of x has the shape of that. Okay, and the function that we're concerned about in options A, B, and C is actually f of x plus f of negative x, right? Remember in like transformations of functions, f of negative x is just flipping this about the y-axis. Okay, so if we add that, what will happen? So let me grab a blue marker and let's flip this like that. So open hole here, open hole here. We have a function going like that, and then we can flip the other ends as well. So like that and like that. So this blue graph is f of negative x, and we want to add those two. Okay, so let's see. Limit, option A is limit x goes to 1 plus of f of x plus f of negative x equals 0. Is that true? Okay, let's go to 1 plus. So 1 plus of the black function is 1, and 1 plus of the blue function is negative 1, right? So it's 1 plus negative 1, which is 0, and the statement is true. Okay, number B, function f of x plus f of negative x is continuous on x equals 1. Okay, so B, so we go 1 plus, the limit is 0, right? 1 and 1 minus. Okay, let's do that. At x equals 1, what's our limit? What's our function value? Sorry. F of x is at 1 and f of negative x is at negative 1, so that's still 0. And at 1 minus, we have f of x going to negative 1, f of negative x going to positive 1. So we have 0 again. So therefore, it is continuous on x equals 1. Functions f of x plus f of negative x is continuous on the set of all real numbers. On the set of all real numbers. Okay, so now we have to verify for every real number. Now on these two ends, it's just a constant plus constant, which is continuous. Now the only points of discontinuity can occur at negative 1 and 1, right? So we just need to check these 2 points. And if we check negative 1, right, the left-hand limit, the right-hand limit, and the function value is all, one of them is negative 1 and one of them is 1. So it's all 0. Therefore, it is continuous on the set of all real numbers because the limit exists and the function value equals that for all real numbers. So that statement is always also true. Okay, so it turns out that A, B, C are all true for that one. The next one that we have to do is number 18. So number 18 asks us about some intervals and some functions. Okay. Function f of x equals 1 over x minus 1 is continuous on the interval negative infinity comma 1. So it's a closed interval and the union of 1 comma infinity. Okay, so if you learned how to draw this graph, then you're probably going to draw this one, right? Something like that and that. Okay, you can clearly see that there's an asymptote at x equals 1. So it's not continuous at x equals 1, but it's continuous everywhere else, right? So yes, this is true. And even if you don't know the graph, right, the only possible point of discontinuity is at 1. And if you go to 1 plus, it's positive infinity, and 1 minus, it's negative infinity, so the limit does not exist. So these two unioned together would represent all possible values of x's where this is continuous. So A is true. Number B, function f of x equals square root of 2 minus x is continuous on the interval negative infinity, comma 2, and this is a square bracket. Okay, so if we want to draw this function, some of you may know how to. I think this is covered in like pre-calculus 11 or 12. I think it's mainly covered in 12. So if we take the negative out, it's x minus 2, right? So we take square root of negative x, which is this function, and then we translate it to the right by 2. It starts here, and then here's our radical function. So it is continuous at 2 because, remember, when we're dealing with closed intervals, the only limit we need to look at is this one, right? We don't need to care about the right-hand limit when we're discussing continuity on closed intervals. So the limit and function value, yes, they do equal to each other. And it's a smooth continuous curve for the rest of the real numbers here. So yes, this is continuous on this interval. Option C. Function, we have x squared minus 3, x squared plus x plus 1. Now, we don't necessarily need to draw this function because all it asks is it continuous on the set of all real numbers? So negative infinity to infinity. And what you can do, remember, for rational functions, we really don't really care what goes on in the numerator. The denominator is the more important one, because if this equals to 0, then we've got an asymptote and we have a potential point of discontinuity. But if we check the discriminant of this bottom function is b squared minus 4ac, which is -3 less than 0, right? So this can never touch the x-axis, but it's a concave up parabola, which means that x squared plus x plus 1 is positive for the set of all real numbers. It will never touch 0. So we can be assured that yes, this will be continuous because it's a polynomial rational function. This will be continuous for any value of x. So all of these statements are true, and that was number 18. The next one is number 20. Select all statements that are true. Okay, so I think I said last class that number 1, try to find counterexamples, and if you can't find any that come to mind, you should think about why this holds true for all possible cases, right? So if we look at statement 1, if f of x and f of x plus g of x, if they're both continuous, then g of x is continuous. So remember the properties, the properties of continuous functions. If you add, subtract, multiply, or divide two continuous functions, then you'll still have a continuous function. Well, assuming that the function that you divide is not equal to 0, right? So yes, because g of x is literally this function subtract this function, right? This function minus this function. So if these two are both continuous, then g of x is continuous at x equals a. So number 1 is true. Now number 2, it asks us about if f of x and g of x are continuous, they're discontinuous, sorry. They're discontinuous at x equals a. Then, is f plus g also discontinuous at x equals a? Right? I think we talked about some ways to get rid of discontinuities, and let's see if we can find a counterexample in this case, right? So one easy counterexample that I found was when f of x is shaped like this. So we have -1 and 1. If we let f of x be a function like this, and g of x be a function like that, at -1 and an open hole, and like that at 1. If this is g of x and this is f of x, look what happens at x equals 0. F of x is obviously discontinuous at x equals 0. G of x is also discontinuous at x equals 0. But if we add them, look at the left-hand limit. -1 plus 1 is 0. 1 plus -1 is 0, so that's the function value. And the right-hand limit, -1 plus 1, is also 0. Which means that f plus g is continuous at x equals 0, which invalidates this claim, okay? So one simple counterexample is all you need, right? Okay, number 3, it asks the same thing, but is f times g discontinuous at x equals a? We can actually use the same counterexample that we found over here. If we go to the left-hand limit, -1 times 1 is -1. 1 times -1, so the function value is -1, and the right-hand limit is 1 times -1, it's also -1, which means that you can make a function continuous even if the individual functions may be discontinuous, okay? So this claim is also false. So the only correct one is statement number 1. Number 21. I think this one was pretty straightforward as long as you know what the minimum and maximum values actually mean, right? If a function approaches a value but has an open hole here, does it have a maximum value in this interval? No, right? Because it's undefined, which means you can get closer and closer and closer to it. But what do we mean by maximum? We mean that it's a fixed number that is at the highest point. No other function value should be higher than your maximum value. And in this case, you can't get a fixed real number as your highest function value. So if you look at the problem, I'll just draw a brief graph. It's shaped like that, and then we have a redefinition here, that, and we have it like that. Okay. Okay, so at intervals, on the interval 1, 2, it's a closed interval. So here's 1 and here's 2, right? So on this closed interval, is there a maximum value? Yes, there is, right? It's right here. It's a closed interval, so we can include this point, and this one has the maximum value. So A is correct. Correct? Okay. B, it has a minimum value on the interval 2, 4. So 4 is over here. It's a closed interval, so now we're looking at this interval. Does it have a minimum value? No, it doesn't, right? Because it's undefined here, right? It's undefined at this point, which means we can get pretty close and we can get closer, but we don't have a set fixed real number as our minimum value. So claim B, that's false. And let's look at C. It does not have a maximum value on the interval 3, 4. Okay, so 3, 4 is also a closed interval that we're looking at, and in this interval, we do have a maximum value, right? Because it's right over here. This value is y equals 3. It's defined here, which means we can say, hey, 3 is the maximum value on this interval, and statement C is also false. Okay, so the only correct statement is A. 23. For polynomial function f of x, f of negative 3 is a plus 2, and f of 1 is a minus 5. How many integers a exist so that equation f of x equals 0 has exactly one simple root in the open interval negative 3, 1. Okay, remember from last time, a simple root is when there's only one factor in the factored form, right? If there's only one factor of like x minus alpha in the factored form of a polynomial, then it will have a graph that looks like this. It will pass straight through without being tangent or anything weird like that. A multiple root could be x minus alpha squared or x minus alpha cubed, or whatever it may be. But a simple root, it has to go through the x-axis, whether it's like this or like that. Because if you can compare the sign as x approaches like alpha minus and alpha plus, the sign here has to be different so that it has to cross the x-axis somehow. And this reminds you of what? The intermediate value theorem, right? If we have the function value at negative 3 and we have the function value at 1, whatever those two values may be, it has to have opposite signs so that we can guarantee, because it says polynomial function, so it's a continuous function. As long as that function is continuous, it's going to intersect the x-axis at least once, right? Exactly one simple root. Okay, so f of negative 3 is going to be a plus 2. And f of 1 is going to be a minus 5. So if we multiply them and they have different signs, we are guaranteed to have a value less than 0. We can't have 0 because we need to guarantee that it's a simple root. Now, a double root might look like this, right? So we can technically have these 2 points and they can be above 0, or if one of them is here, they can be at 0. But we have to have a simple root, so this case does not work. So here we can solve the equation and say negative 2, a 5. So it's 0, 1, 2, 3, 4, and negative 1. And that is 6 integers, a, that you can find. Okay, final one, number 24. I think I can get away with writing it here. Number 24, a train departs from station A and makes 2 stops at stations B and C. The maximum speed of the train while traveling between stations A, B, and B, C are both 60 kilometers per hour. At least how many times would have the speedometer on the train read 40 kilometers per hour while the train traveled from station A to station C. Okay, and the train does not stop in between stations. So if we draw a speed versus time, right? Speed versus time graph of the train, we can say that between stations A and B, you have to start from rest, right? You have to start at the speed equals 0, you have to accelerate, and then at some point you gotta slow down again. It's a continuous curve, right? Trains don't magically, jump back and forth between different speeds. So the maximum is 60. So I can say that, hey, the maximum is 60 and it went from 0 to 60 and back, right? We know that this has to be 0, this has to be 0, and at some point it has to be 60. What happens in between, we don't know, but we really don't care because we're saying at least how many times. So we just want to have the simplest possible scenario. And then stations B and C, it's exactly the same thing. So it has to go up and it has to go down at some point, right? This is inevitable. Okay, and now we have to find 40. And then how many times would have the speedometer read 40? At least, how many? 1, 2, 3, and 4 times during the train's journey, it would point to 40 kilometers per hour. Okay guys, so this is the end of Unit 1. So if you made it this far, congratulations. You're well on your way to building like a very strong foundations for what's about to come. So the next unit, it's going to get really, really interesting. We'll learn a lot of new concepts as well. And you'll actually start to really analyze functions, which is the whole purpose of this course, okay? So the unit test we'll have on Thursday. I think some of the IB kids already wrote the unit test. So just remember, when you're studying for this, don't memorize the exact question because that doesn't really help, right? The unit test questions will be something that you've never seen before. But what I do want you to remember is what are the ideas that you use to solve some of these problems, right? What made me to perform this action at this specific problem? Because of what, right? So think about the ideas that you use to solve the problem and remember that you now have all the tools that you need in order to solve complicated problems. So carefully reading the question, carefully picking out those individual conditions, even if you think it's like a tiny insignificant condition, everything is given to you for a reason, especially in math, right? Okay, so I wish you the best of luck on studying. I hope you will write the unit test on Thursday. After Thursday, I'll upload the PDFs of the unit test and I'll have an answer key as well. And in next class, we'll go over the solutions to the unit test, okay? So good luck studying. Goodbye.